Hello, good morning or good afternoon to everybody. That's the lecture that I promised to you. Instead of giving on the lecture room, I'm providing as a video lecture. And I hope you all have time this week to follow this lecture to complement the topics that we are discussing on the light-matter interaction, right? Interaction of radiation with matter. In previous lecture, I have discussed with you a model that's called classical model of light-matter interaction. Why is it called classical? It's called classical because in that model, we consider the light as a classical field oscillating. We don't speak about photon, individual photons or things like this. So we don't really quantize the electromagnetic energy in packages of photons. And also, we consider the charge that's coupled to the matter on the orbitals as something that, even though we know they have different shapes and different things following the quantum concepts, but we did not consider that. The model that we present was that any amplitude of field I can put, I can afford any deformation, any displacement of the charges present on the matter. And based on that, we construct what we call the driven and damped harmonic oscillator model, where we put energy, the charges may shake around, change, oscillating around the equilibrium point, and that's the way that energy is coupled from the electromagnetic field to the molecules, to the matter in general. And then we end by having many effects that's coming on the applications we're going to explain to you in further lectures about the biophotonics applications. But one thing I told you in the very beginning is that actually the charge distribution on the matter is not anything and cannot be deformed any way I want. When I apply light, I told you, wow, this will displace from the center of mass of the electron cloud, will displace, and that's the way that we oscillate because the field of the electromagnetic field oscillates. And I didn't put any restriction on that. But actually, if you look careful, that's not true. Nature does not let us to deform a distribution like this the way we want. Not in the atomic and molecular level. Normally, there are distributions that are allowed to be possible, because of the nature of the electron in the matter, it's waves. And as I told you, I cannot accommodate any wave in any way that I want in the orbitals. There are specific distributions that they obey. And when I add any interaction by the light with those charges, they cannot do anything I want. They cannot displace, and that's it. They have to either deform in a way that it has to be a composition of the possible allowed orbitals. Allowed by whom? By quantum mechanics. So actually, when I introduce this modification, I go from a full classical treatment. Everything is possible. A classical equation of motion is possible. Because, if you see what we did is consider a mass. We charge the electron mass, the charge of the electron being displaced around under the influence of the electromagnetic field. Now, we cannot do that. Only a field distribution are possible. So that change the way to treat. I cannot have the equation of motion for the charge distribution following a model of driven damped harmonic oscillator. Now I needed to treat the problem in a different way. considering the possibilities and the superposition of possible solutions for the problem. And that means that the matter now is fully quantized, but the field is still classical. The electromagnetic field is still there, and we call semi-classical because we are not treating the electromagnetic field, the light, considering photons, but we are considering the matter by packages, by orbitals well predicted by quantum mechanics. What changed in this treatment? Well, changes a little bit because now I cannot have an equation of motion that will show the amplitude of the deformation of the charge, as I did extensively with you for you to understand the scattering, classical scattering of light from matter, Rayleigh, resonant, Thompson, and so on. Okay, so today we're going to evolve, so as you can see in the transparency, we're going to evolve to the semi-classical model. And it's one of the last lectures on the basis, on the physical basis, where I am giving physical principles for you. And then I'm going to start a little bit about biology and then go to the applications, which is the most interesting part of the course. But we cannot do application if you know the basis, right? Nobody applies what they don't know. So I'm trying to give you all the background, and then we're going to go to the applications. Very good. So I'm going to consider this now. So we see the transparency. And I cannot treat the charge as a center of mass displacement. I have to consider what nature, the quantum nature of matter allows me. So if you remember this, what you see here in this view graph, in the first slide, it's just the possibilities of orbitals that the quantum nature of matter allow me to have. So anything I do now has to be expressed by the distributions that are permitted. So let's start, and the first thing I want to do, we're going to call this semi-classical model of light-matter interaction. And why semi-classical, as I told you? Because in the classical model, we have considered an oscillator which any amplitude is possible. Any amplitude of oscillation of the center of mass of the charge present on the matter was possible, and we are able to find a resonant curve where the amplitude is the dominant result of this interaction. Higher amplitude in some frequencies means that more energy is transferred to the matter, so we say that there is more absorption of energy by the matter. In the quantum model, we have to change a little bit. We're going to have to consider that not everything is possible on this charge distribution, but only a few possibilities that we call the orbitals. So quantum mechanics, when we solve the problem of the electron attached to the matter, attached to the nucleus, attached to the molecules in general, we know that only a few distributions are possible, and that give us origin of the orbitals. So we're going to consider then the matter as quantum and the light as classical, and that generates the semi-classical. This is still possible, and it's very good. I think this is one of the most intuitive things we can do. But now, your picture, what you have in your intuition, has to change a little bit. We need to imagine an orbital, and we're going to apply the field. I represent here electrical field of the radiation up and down, and that they're going to interact with the orbital. And of course, you can see there will be also interaction. Normally we work with the dipole interaction. So still displacement of charge. When charge is displaced, there will be a dipole because negative charge will be somewhere and the positive charge of the nucleus will be in another place. There is an electrical dipole associated with this interaction, and normally we call dipole interaction. But you can imagine now the following. Light will interact with an orbital, like the S orbital. Okay? And in this interaction, there will be a possible deformation of the orbital, because there will be a interaction. There will be an equivalent, let's say classically, to a force that the electromagnetic field is putting on the orbital. And that may deform, but this will happen only if the deformation of this orbital looks very much like another possible orbital allowed by the quantum mechanics. So here I just to simplify, putting the S orbital, which is a sphere of charge, not homogeneous, there are charge more in the center and then decay. And then when the electrical field of the light interacts with this, may take the charges to up and down. And that is easy to imagine that will be looking like a p orbital, because the field when it's down will make the electron cloud go up. When it's up, you make the electron cloud go down. So actually you go from a sphere to those two bumps that characterize the p orbital. So if this interaction is such that whatever the light is doing looks like the p orbital, then this interaction is allowed. This interaction is allowed, and probably there will be an electronic transition. When that happens, so you take one orbital and the interaction with light deform enough to go to another one, then we have an electronic transition. If I make a tiny variation, then what's happening is, actually, because the system can only be in a few orbitals, so whatever is the new distribution has to be a sum with different weights of the existing possibilities of orbitals, right? This is what we call superposition of orbitals during the interaction with light, and it's the base of many, many, many things, including the new quantum computers and things like this. Okay, so now in your imagination, you have to remember that, semi-classically speaking, the electromagnetic field will interact with the matter only if it takes from one orbital to something similar to the other. So you have to deform your distribution in a way that it looks like the next orbital, allowed. If it is something fully different, it will not take place. The interaction will not take place. Right? Okay, so if you have this in mind, if you start to think that you understand this, let me remember to you that the atomic orbitals are solution of the master equation of quantum mechanics. And this equation does not treat, it's still an equation based in energy, but for us, the energy is represented in a different way, because now everything is a wave. So all the solution, all the electron cloud is represented by a wave. So if you remember, to characterize a wave, we need frequency and wavelength. And to characterize a particle, we need energy and momentum. So we're going to convert in quantum mechanics, because we're dealing with an electron that traditionally is a particle, we're going to have to convert this in what we call frequency and wavelength. But the wavelength is associated with momentum and is spatially variation. So instead of having kinetic energy, which is something associated with momentum, we're going to have a variation in space of the function that represents this quantity, the co-electron. And because the frequency is associated with energy, the time oscillation of my solution is associated with the fact that my system actually has an energy, right? Associated to it. So this important master equation I already showed to you briefly when we discussed in class, and is written by this. This is nothing more than kinetic energy plus potential energy equal to the total energy. This is what this equation is. It's called Schrödinger equation, but actually it's telling me that variation of this wave function in space, which is represented by the second derivative, plus the potential energy has to be equal to the time variation, which is the total energy of your system. So I compose the kinetic part, which is the momentum, with the potential part, which is represented by a potential that's keeping the electron in there. In the case of atoms, will be the Coulomb potential, right? The attraction by the nucleus, the electrostatic action of the nucleus. And this has to be equal to the time variation, which is the frequency, which is the total energy. So that's an equation that represents conservation of energy, but expressed for waves. Expressed now considering some principles that was built up in quantum mechanics. But the solution is no longer a trajectory as it was when I treated the electron as a spring and mass. Now the solution will be a collection of possible functions, with spatial variations, which is called wave function. And knowing this wave function, I can solve the problem, because this wave function, this collection of wave function, it gives to us exactly the possibilities of solution of the problem. What waves can be accommodated in this problem? And those are the orbitals normally when we're treating electron either bounded by one nucleus or bounded by many nucleus in molecules. The solution that displays that cloud of electrons has to be represented by a wave function now. And that's the basic of the quantum mechanics. Why is that? Nature is like that. It's not that we imposing this. No. We observe that that's the way it is. And then we follow that. And we keep it going and understanding what's going on. So the beginning of this discussion is that I have a collection of distributions. We call the orbitals. And normally for us, the wave function is the beginning. But the wave function is square. It gives us what is the real spatial distribution. When we multiply by the charge, we have the density. How the charge is distributed. And as an example, as we consider the potential, as I am presenting here, the Coulomb potential, we know already that you can predict many different wave functions, which square will give you those nice figures that we always learn as being the atomic orbitals, which is nothing more than the charge distribution spatially represented for you. Normally, a physical system has a collection of possible distributions. In your case, the atom, the electron, so the charge. In the case of a particle, any particle will be the distribution of mass. So each orbital, in fact, has an energy, because if you go back to the equation, for each time spatial variation combined with a potential. So if you go back to here, each potential, which is a potential, is fixed. For each spatial variation, we're going to have a different energy. Look, the energy is the sum of those terms. That's why different orbitals represents different energies, because they have different spatial variation, even though the same potential is there. But because I'm allowed the different spatial variation, I end by having different total energy for the system. Okay? So that's the basis for us. Instead of treating that we have a distribution that's very much like an oscillator, now we cannot do that. We have to treat the distribution as discrete. That's why it's quantized. It's discrete. I cannot have anything. I only need a few, which is the solution. It's what nature is allowing me to have as the wave nature of matter permits. And this is given by this fantastic equation that this next year is commemorating 100 years of existence and modify completely or understand about everything around us. Okay, So let's simplify, because we all know that an atom or a molecule can have many, many, many energies. You learn even in high school that, you know, when the electron is in the nucleus, the hydrogen atom is the simplest. You can have many, many energies allowed, which means many, many waves, many, many spatial distribution possible for the existence of the electron in that configuration. But we're going to simplify now. Let's assume that only two is very important, and especially because when we're dealing with light, the energy of light will not match any possibility of transferring energy. Normally, the energy of light will match a few levels. So I go from here to there, the energy of the electromagnetic field has to match with the energy of the levels. So we're going to do what we call two energy level approximation. Even though we know that matter has many infinite energy levels, but because we're going to be working around one possible transference of energy or transition, as we like to call, we're going to consider two levels. So we're going to hypothesize that our atom is actually a two possible waves representing the existence of the atoms. And nothing else. The atom cannot be anything. The distribution of charge cannot be anything besides these two possibilities. What are we going to call psi1 and psi2? But this is just two different spatial distributions. And by solving the equation, we can show that the solution has a part that represents the spatial distribution, which is the kinetic part, and another one that represents the time variation. But because the potential is not time independent, we find always the same solution for time, which is an oscillation, which represents a single frequency variation in time, which is a fixed energy. That's why we have levels with fixed energy in the quantum solution of the problem. So we have two possible energies in the system, right? In the quantum system, and now the light will come. The light also is represented by an energy represented by the frequency. So whatever the energy of the light matches the energy that the system has to receive from going from one state to the other, those jumps, those transitions will take place. So now the energy will be transferred to the matter, but not in any way with any amplitude, only if this became possible. And sometimes, depending on the frequency of light, you can transfer a little bit. You can make the cloud looks more like, we're always going to start to the ground state, which is the energy of the lowest state, that here we call 1. And then sometimes if the energy of the photon does not match very well, we're going to just mix a little bit of the possibility of the second level to the first one. Everything now will be a question of mixing, superposition, like we like to say in quantum language, let's say. So don't worry too much about the solution. This is what's come out from that equation I showed to you, which is the master equation, we call Schrödinger equation. And but you have to understand that it has a spatial part and has a time part. And the time part only means here, because it's a single frequency, exponential of I to the, because it has a determined frequency, has a determined energy of the state. That's what this represents. Okay, now we're going to consider two, and let's get the two first orbitals. We know the s orbital and the p orbital. And now we're going to interact with light. And when interact with light, as I told you, the light, if you imagine in a classical intuition, you don't need to, but if you imagine, this spherical distribution, which is the ground state, is where the matter is sitting in the absence of light, will start to evolve to the next possibility, which is the next orbital, because the electron field is able to displace somehow in our classical intuition to deform the orbital S in a way that looks a little bit like the p orbital. And then the interaction is taking place. Normally, because there is a change configuration of charge, there is a dipole involved. So the total interaction energy is as if this was like a dipole, right? Because the charge is here, suddenly is there, and this will be an oscillating dipole, performing the two bumps that makes the p orbital. I hope everybody's following me. It's simple. I'm being as simple as possible, less mathematical as possible to explain to you this quantum nature, which somehow is necessary to explain many, many things. So, actually, we could resume everything I told you so far, saying that the field of the electromagnetic, the light, promotes charge displacement, but not any possible. Has to go from one to the other. But maybe it's so tiny that will be 90% of the one and 10% of the other, so on. But that's what this will produce. But if you measure, it has to be in one of them, because those waves, as I told you before, has an interpretation of probability. And you'll be able to say, okay, I absorb a little bit of light, so I have a very little chance to detect my system in the orbital 2, in the state 2, instead of state 1, and so on. But if we assume that all the solution in the world has to be composed of these two states, we can go back to the original master equation and add now the interaction with light, which is a dipole type, because there will be charge displacement. And we can solve the problem. I'm not going to do it, but we can do it easily. And the action of the field actually will do what I call a displacement. But the displacement has now to be a combination of these two, because that's the only two solutions allowed for the charge distribution of the atoms. It's not like the way I solved before that, the amplitude of the oscillator was building up. Now, no. Now, either you have this plus that, or pure this or pure that, but has to be the only two or composition of those two. Because what I'm doing here is a displacement of charge with the electrical field, because the electrical field times the charge makes a force and displace. So whatever this integral of the wave, spatial wave that represents one orbital and the wave that represents the other orbital, with a displacement in between is different of 0, means that I be able to transfer energy to the system. That means in your language that the transition from the state 1 to state 2 is possible. Interesting. Transition from state 1 to state 2 is possible. And you see, if you look at this integral, one of those days I have to do a physical interpretation, but this is like the potential or the displacement acting in one state will make it look like the other state. Basically, that's what we have here, right? This is the conventional interpretation of this. And we normally say that the quantum concepts works a lot with mathematical operators. In fact, they are not mathematical operators, they are physical operators. You do a mathematical operation that represents some physical interaction. And here, what we're doing is displacing orbital 1. If it looks like the orbital 2, this integral will be no zero, which means that this is like I'm projecting with the interaction the state 1 in state 2. So like a vector that was orthogonal to the x-axis, and now I start to tilt it. So it means that it has projection in both axes. So this is what's happening here. Okay. So action of the field in the state 1, which I consider the state that was there before the beginning of the interaction, now can be anything possible solution in the system. So it can be a composition of the orbital 1 and the orbital 2. And the whole problem is not determining who are the solution, because this you know before. You know before the orbitals that are possible. Now, the problem resides in determining how my light will produce different composition of these possibilities. So we say that the overall solution is a sum with specific coefficients of the solution 1 and the solution 2. Because those are the two possible solutions of your problem, quantically speaking. So you see, the problem changed the face. Because now when I put light, the only thing I can say is, well, there is if I have a A1 coefficient that's big, the system will stay pretty much on the state that was born, the state 1. Now, if the A2, the coefficient of the second state, is growing in time in the presence of light, means that there is a big chance that the system will be in state 2. Or the energy will be coupled to the system. I will transfer energy to the system. Actually, the interpretation of A1 square is the probability that the system, if you make a measurement, the system is in the first state. And the A2 square is the probability that the system stays on the second state. And of course, since they are probabilities, and the system has to stay in one or the other state, means that the sum of A1 square plus A2 square are 1, a unit. So I turn on the light, shine this quantum system. It can be 1 or 2, or a sum of them, a superposition of them. But the sum of the probabilities to be in one and the other has to be 1, because it has to be in one of those. Those are the two solutions. That's everything nature allow your system to be in one or in the two. Or in a superposition, but a superposition is just the probability of being 1 and 2. So that's the concept that change when we treat the light-matter interaction in this level. Okay, so what's happened actually when we visualizing what's happened, the system, when I turn on the light, my system starts to deform in my orbital S, which is the circular one, which originally A1 square was 1, so means that was 1. So the system was actually in the state 1, represented by the orbital S. And that's why it's dark. And then as I keep the interaction, my system is starting to deform. And then I started to have a composition, a sum of distributions of 1 and 2. So the probability of being in 1 starts to decrease, goes from 1 to 0.7. And the 2 that was 0 start to be 0.3. It's always with A1 square and A2 square equal to 1. So then what's happening is my orbital that has the 2 bumps start to be dark. Now there is a big chance that the system will be in that orbital. And then if I keep the interaction going, as the time passes, more energy will be coupled. And then suddenly you see the system fully in the orbital 2. So the 2 bumps now is fully dark and the spherical one is empty, right? So as the things evolve, I'm transferring the probability of being in one state to be in another. And then suddenly A1 square is 0 and A2 square is 1. At that moment, I say that a full transition took place. And if I stop the light there, all my atoms, all the absorbers of this sample will migrate from state 1 to state 2. But if I keep the light going, what's happened? Happens that the same way that I act on the spherical distribution, to take the system to this elongated distribution. Now I work back. I start to compress the elongated distribution, putting back the atom in the orbital 1. So I can transfer, and then the system can come back. The light can make the system come back. And where this energy went then? Went back to the electromagnetic field. So the system actually can oscillate between being in state 1 and being in state 2. And 1 and 2 is the only thing it can be. But in between being fully in state 1 and fully in state 2, there is a superposition of being 1 and 2. This is the beauty of the quantum mechanics that allow us to do wonderful things. This is called the superposition of states, or coherent superposition of state. Because if I stop my light in between, when I had a chance to be a little bit in one, a little bit in the other, they're going to stay that way forever in life. So that's the difference between the quantum matter and the classical matter. Classical matter will shake around. Quantum matter will superimpose the possibilities of existence of the electron cloud, which in this case is two possibilities: state 1 and state 2, two spatial distribution, elongated or spherical. Is that clear for you? I hope so, because you see, A1 square plus A2 square, which is the coefficients of the superposition, is always 1. And as you saw in the picture I show, the system will oscillate between one another because the same electromagnetic field can take a sphere to elongate it and can bring elongated to a sphere. So the system oscillates. And the frequency of oscillates depending on the field I'm adding to the system. The electromagnetic field, the electrical component, in fact, of the light, times the electrical dipole. Because that will tell us how much is this interaction, because now involved displaced. It's like the energy of a dipole. And it divided by h give you a frequency that's called Rabi frequency, which is basically the frequency of oscillation of this probability between the two states. There is a natural frequency of the system, which is the energy of the second state minus the energy of the ground state, the E1, divided by h. This is the natural frequency. And the frequency of light may be different of this natural frequency. And this difference we call the detuning. How far the energy of the light or the frequency of light is from the natural frequency. Because in quantum mechanics, energy means frequency. Energy means time variation. Energy means whatever is the component of the wave that varies in time, which is represented by the frequency. The existence of a frequency of variation. So everything make a very nice contest here. Okay? So with those definitions in mind, we can actually solve exactly, I'm not going to do, but we can get how is, once I turn on the light in t equal to 0, and the system is in the level 1, I can see how the probability of being state 2 or state 1 builds up in time. If you put t equal to 0, of course, A1 is 1 square and A2 is 0, because A2 is just a sine square. And the amplitude of this depends on the what I call Rabi frequency. It is the coupling of light with still proportional to the intensity, because omega is proportional to the electrical field, which is square is proportional to the intensity, as I'm showing there in the corner. And then is still proportional to the intensity, still in what we call linear concept. So that's the variation if I solve the master equation. If I take the wave function, put back in the equation, and solve, I will see that that's the natural evolution. But you know, graphically speaking, what we're going to do as we turn on the light, A2, which is the probability of the system have the being in the second state is 0, and that builds up and oscillate. If it is delta equals to 0, it's going to oscillate between 1 and 0. Is missing a 1 here, the maximum of this oscillation. But if delta is not 0, remember, when I take the frequency of the light far from the natural frequency of the oscillator in the full classical model, the amplitude was small. Here, the amplitude of probabilities is small. So the chances for me to go to the second state is lower. And as I go further, so I put a delta equal to 1, which means not 0. I'm going far from the resonant frequency. If I go even further, it's a smaller oscillation. Faster, but smaller. So when I turn on light in the quantum concept, I turn on the light. I turn on the light. The system starts to oscillate between the two states. Actually, it does. Oh, is the probability? Yeah, but if I make a measurement, that's what I'm going to find. So the system oscillates between two, and this is called coherent superposition of the states and coherent oscillations. That's the base of many, many, many things in physics, including the atomic clocks, including everything that you are using in your telephone. That is an atomic clock. Synchronize every transmission of information. You don't even know that everything I'm telling you is in your real life. Okay, so that's what's happened. That's what I have. So normally you see in the books the picture of this two-level system, radiation coming in, coupling these two states by this oscillatory behavior that I represent by this arrow. And you know, that thing that I explained in the full classical model about emission of radiation, here also takes place by different reasons, by the uncertain principle. So now, and in fact, the presence of the vacuum is a little more complicated justification. But the system can just, because when the system is oscillating in the coherent superposition, energy goes from the light field to the matter, comes back to the light field, goes back to the matter. So it's an oscillation. And people measure this. The energy comes to the light, goes from the light to the matter, comes back from the matter to the light. So that happens, that oscillation, that coherent oscillation that I told you. But the dissipation takes place. Eventually, light will be emitted everywhere. And that's called spontaneous emission. And that happens in some rate. So as I build up a population, I have a better chance for that to put energy out in this spontaneous emission, which is a kind of dissipation, as just giving a similarity with the full classical model. And therefore, because of this dissipation, the system then cannot oscillate forever, because there is a moment where any energy I try to put to make the oscillation is lost. So if I really look at what's happened when I turn on interaction of the light, classical light, with the quantum system, it oscillates in the very beginning and then dumps out and stay in a value. And this value represents end of the oscillation. And that is what we call the stationary probability of the transition. That's the stationary, let's say, absorption probability. Whatever this A2 square value turns out to be in a long term, I turn on the light, there is a fast oscillation, and the probability that the energy be coupled on that level, that you make a measurement and find the system in the level 2, is given by this expression that also we can obtain. Remember, this is what we call a full Laurentian shape. Actually, as a function of the frequency of light, it grows symmetrically. Classically, the classical model is not full symmetric, but the quantum one, or the semi-classical one, is full symmetric. So the probability of the transition, that basically this times the power that you put in, the intensity you put in, is the power that's absorbed. The probability, which is this shape, times the intensity of light, is the probability that you deposit for one single two-level absorber. If I have any, I have to multiply by any the same way we did. The same way we can now calculate cross-section of absorption. We can calculate all this. But it is necessary for this to have this dissipation that's given by spontaneous emission. The spontaneous emission gives origin to the fluorescence of the things. Okay, spontaneous emission gives the origin of the fluorescence. Or the light you see things emitting all the time. Sometimes you turn on the light, this reaches already the regime and you see the brightness of any object because of the light that's coming to you and is not being incorporated in the light field again. So this is a semi-classical model. We are able to find the line shape of the absorption, which is basically the probability of absorption. But that's natural. Always you have a probability times the quantity, you have the overall average quantity that absorbs. So that's the expression you have to keep in mind. And omega, big omega R, that's the Rabi frequency square. Normally you can represent by the intensity. That's proportional to the intensity of light, right? The intensity times a coefficient. Now, what's happened when I have a very, very big intensity? Means omega very, very big. So the only thing that stays is omega on the numerator and the denominator, and that they cancel, and the probability is half. So when you put a very intense light, the probability of finding the system in level 1 or level 2 is half, even with dissipation present, but intense light is half of the time the system is in one state, half in the other. So then when you measure, your probability is going to half. This is what's happened, this term. Now you have to multiply by density, by intensity, everything, to have the overall absorption coefficient. Spontaneous emission is fundamental here because it's the origin of a fluorescence. And if there is the dipole is equal to 0, this is what we call a forbidden transition. They don't take place. And then you need the high order transitions. And then they comes not the dipole, electrical dipole transition, but will come quadrupole and everything. This oscillation is very nice. This transmission of population is very nice because that's going to give the beginning of the laser. The laser light is when I produce, how the laser light works in the following way. I turn on light or some excitation, I transfer all the population to the top, and then I put a seed photon, and everything comes down, and then I amplify the radiation by giving all the energy of the matter to the radiation back, the same way of the oscillation that I showed to you. That's how the laser works. Okay, so here we are again. We finish one more lecture. Let me put the first transparency. It's wonderful to have this transparency showing that this is the lecture notes 9. It's not the 9th lecture. I mean, I gave already many, but this is the set of lecture notes 9. There will be also a notes on this written, so in a way that you can understand, so you have a better chance to reflect, right, to think about, because it's important, understanding the classical model helps a lot, our intuition and everything, but the semi-classical actually allow things that the classical will not, including saturation and different effects that happens. And then if we're not going to do it, but we could now quantize the radiation. So now photon by photon will go, and the light can also be quantized, only a few configurations, and then we have a full quantum model for this interaction. But for most of the things we're going to do, this is a great system this is a great point to stop. So today with this lecture, I'm closing all the background of light matter interaction. And then in the next lecture, that's the lecture for this week. I hope in the next week you have a good vacation, 2 days break, and then we come. I have to give a very nice lecture on the biological basis. What's there in the cell, in the tissue, that make light interact, that can make a difference, right? Can change metabolism, can change energy, can make it disruptor, can make the tissues fly apart or being vaporized. And this is what we're going to build up in this concept. So I hope you can see the lecture more than once. You can really capture the picture of this semi-classical model. It's a concept. What I want to transfer to you is a concept. And then, of course, you'll be able to understand many of the things we're going to do when this concept are needed. So thank you very much. See this lecture this week, and see you next week. Bye-bye.